So we're just going to discuss, again, just very basic kinetic versus potential energy concepts. Kinetic energy was the one that was the most discussed, in my opinion. You were told what the formula for it is. Just kind of talks a little bit about the different types of energy, and then we presented a scenario where there wasn't a perfect transfer of energy from kinetic to potential because some energy is always lost due to heat. And this whole chapter is about figuring out where that heat goes, where it's coming from, and calculating different pieces of information using that heat. We were introduced to the energy unit. As the joule. We also had a very brief discussion on calories, little c calories versus capital C calories. These are the ones on your nutrition facts. These are more heat related. We did a lab calculating these different calories for energy content or energy content per food sample using that burning of the junk food. I'll remind you of that. Where you tried to figure out exactly how much energy does a single Cheeto contribute as far as calories are concerned, amongst other things. We then talked the first law of thermodynamics. Okay. That first law talked about change in internal energy of a system. This one basically stated, for our purposes, that change in energy would be directly related to heat and work. So total internal energy change can be related to heat and work. There was a discussion on sign conventions as well. So if Q is negative versus Q is positive, this is where we introduce terms like endothermic and exothermic. This is where we introduced terminology, I would say, or kind of ways to talk about heat. So we talked about systems and surroundings. Q would be positive when heat was transferred from the surroundings to the system. And this one, Q would be negative when it goes from the system to the surroundings. Okay. In an endothermic system, the heat is going to be absorbed from the surroundings and in an exothermic system, in an exothermic system, yes, I said that right. This system is going to release heat. So the first half of chapter 5 introduced a couple of different concepts around heat and how systems behave versus surroundings. I'll remind you that systems were defined as like whatever you're studying. So think of whatever reaction you can, put it in a box. Anything outside the box is the surroundings. Anything inside the box is the system. Okay. From there, we also introduced a concept called a state function. You better remember what a state function is. Go ahead, Zach.
Isn't it a factor that's unaffected by everything else?
Correct. So it's independent of the path. What that means is that things can take a very long journey to get from point A to point B, but a state function doesn't care about the journey, it only cares about the beginning and the end. Okay, and we introduced delta H as a state function. Anybody remember what delta H is? It's just heat. That's all. Delta H is just heat. Energy generated in the form of heat. Okay? The state function itself says that we don't care if we started with reactants A, moved to B, then went to C, and then ended at D, right? We don't care about all of these different paths. We just care about the delta H from the beginning to the ending point. Does it matter that it takes these separate paths? Maybe if you're trying to study the mechanism of the reaction, but for instance, if we have a mechanism that goes straight from A to D, whatever the delta H is here should be the sum of the delta H's for all the other individual steps if you're trying to get there. And that was Hess's law. Okay, so this is delta H. Next thing was the calorimetry stuff that we did. All I'm going to say is what we just did. That's what calorimetry is. Measuring heat using mass, specific heat, and change in temperature. The temperature can be in Celsius or Kelvin. It doesn't matter. For the most part, I would keep it in Celsius because our specific heats are typically given in degrees Celsius. And like we said, while the scales are offset, right? Like the Kelvin scale is 273 degrees different than the Celsius scale. 1 degree Celsius is still the same as 1 degree Kelvin. You try to convert 20 degrees Celsius to Kelvin, and then you convert 21 degrees Celsius to Kelvin, you are going to get a difference of 1 Kelvin between those two answers. And that's what I mean by 1C equals 1K. All right. Big conversation in the calorimetry chapter on specific heat of substances. Most substances have pretty low specific heats because they don't hold on to heat very well. The exception, of course, being water. Has one of our highest specific heats, really good at grabbing onto energy. Takes a lot of energy to grab, but once it has it, water's going to hold on to it pretty well. Okay. This explains things like lake turnover. If you are a fisher, you probably heard the term. Oops, sorry. You probably heard the term lake turnover before, but the reason why the water underneath the lake is not always completely frozen has to do with the specific heat of water. Okay. All right. From there, Hess's law. We did some Hess's law problems. Over the course of several chapters, we introduced ways to calculate delta H. Many ways to calculate delta H, right? We said delta H of a reaction could be calculated one of several different ways. In this chapter, we introduced Hess's law. Hess's law states that the sum of several steps of a reaction could be added together to get the final step of that reaction, or the final delta H. Sum of delta H of multiple steps. This is one of those where we said, okay, if we could add let's say our goal we were given, remember we had a goal reaction was, say this is our goal. In this particular case, we said that we could flip reactions, but if we flip reactions, what do we do to the test sine of delta H? We flip it. If we wanted to, could we multiply any of those reactions by 2 or 3 or whatever integer we wanted? Absolutely. All in the pursuit of getting to our goal equation. If we just add these together, we should just get this, right? We said that there were parts that could be ignored or canceled out if they were on both sides. We called those, what, does anyone remember? Special name. I believe. Spectator ions were from precipitation reactions and other ionic equations were close. I believe we called these guys intermediates, but that's okay. I don't care. So, that being said, A plus B plus C makes D. In this case, since all I had to do was add the two together, what would I do to delta H? Add them together. Hopefully I did my math right, did it in my head, really bad at
I
that.
feel like we should do like a more complicated one.
Oh, there are definitely more complicated ones to do. Okay, so that was Hess's law. Let me get through as much as I can today before I do specific quests. I want to go through the chapter and then ask. All right, then from there, this chapter, yes it did. We talked about how to calculate the enthalpy of a reaction from individual parts. Products minus reactants, correct?
Yeah.
So that if we wanted to, we could calculate delta H using each individual reactant and product, provided we knew, let's make this a gas, their states of matter. In which case we could add up the products. Where do we get these numbers from? Table. Grams, or gas, sorry, in parentheses. States of matter you had to have, right? Because those tables were all listed by states of matter. Yes?
Will all tables be on the test that we provided?
If you were doing a problem like this, I would give you those numbers. For sure. Absolutely. This would be what, CO2? Do the coefficients matter? Yes, they do. Whatever the value for O2 gas is, you would multiply it times 3. Whatever the value for H2O is, you would multiply it times 2. Same thing for CO2. Okay, from there you would do adding up the products, subtract the total of the reactants, and that would get you the delta H for this specific reaction. You subtract them. This is this formula. Okay. And that was chapter 5. Okay, so far, go ahead.
That equation, that's standard enthalpy change.
Say again?
That equation is standard enthalpy change.
Yeah. Yeah. Enthalpy of a reaction given individual products and reactants. I got Hess's law, and then an enthalpy problem. I'm going to take requests for problems you want me to do from the chapters as we go, but I do want to get through chapter 6. Keep in mind, this is all time-based, right? You have today for me to go through as many of these things as possible. I'm assuming that we're okay, I would say okay, on chapters 11 and 10. 11, for sure. With our intermolecular forces from last week, we went over that pretty much a lot. So 10 is what I have to get through by the end of tomorrow. And tomorrow is a shortened day because of your whatever. Because of whatever. I will be here tomorrow at my normal time, probably maybe like 8 o'clock instead of 7:30. But if you want to come in when all of those kids are doing their finals workshop, and you're not working the finals workshop for some reason, is anybody not working the finals workshop? So a few of you, right? If you want to come in and you want to ask questions and you want to go over specific things over something that you're really struggling on, that is a good time to come, right? So, time wisely. That's the end of chapter 5. All right. Chapter 6 was formulas. Chapter 6 was, remember, the electronic structure of the atom. Specifically, we introduced orbitals, what they look like, how wave properties become orbitals. I will write this down and maybe I can come back to it towards the end of class. Is that okay? The other thing is the freshman finals workshop going to go the entire hour and a half?
Yep.
Woo. They're nervous Nellies. I've got lots of them and they're pretty nervous, so. I mean, that's not true. There are some that are worth more than that, that's for sure.
Wasn't a Spanish one?
Not like they're taking Spanish classes.
Okay, so some different basic equations from electromagnetic radiation. The spectrum of radiation, remember, goes from less harmful to most harmful. Least harmful being radio waves, most harmful being gamma rays, and everything in between. Visible light is somewhere in between. The spectrum is organized by wavelength and frequency, which are, of course, inversely related. As one goes up, the other goes down. Talked about wavelength is the distance between two peaks of a wave. Yes? For which one? For this one?
Yeah.
This is the speed of light. So this is
3.0.
3.0 times 10 to the 8th. This one is, again, frequency. Oh, wait, did I? Is that speed? What did I write?
Meters.
This is supposed to be E. Like, did anybody else notice that I wrote frequency equals H times frequency? Okay, cool.
No.
Yeah. This one is also frequency. H is a constant. Times 10 to the negative 34th. This is Planck's constant specifically. So C equals lambda V can be used to calculate wavelength or frequency given one or the other, right? This guy can be used to calculate the energy of a photon of radiation given frequency specifically. Okay, we also then derived this one. Is it C if I remember? That lets you calculate the energy of a photon given wavelength instead of frequency. So we had two equations where you could calculate the energy given either wavelength or frequency, depending. All right, here we go. Ground state, excited states. You remember what the n values mean? Those are what type of numbers? Starts with a Q. Quantum numbers. These are specifically energy levels. N equals 1 is always the ground, lowest energy level, if you will. We talked about what happens when an electron moves from one to the other. And then we talked about what happens when the electron moves back down. In order to move from one to the other, it has to absorb energy, absorption, if you will. When it relaxes, it releases energy. This wavelength of light typically has a color. This is where we tested the colors of metals and flames. Okay? The color that came out is the emitted wavelength. Do-do-do-do. Quantum numbers. All right, let's do this. Okay? A couple of different topics in between this and quantum numbers. One is the Heisenberg uncertainty principle. Says we don't know the position and the speed of an electron at the exact same time. We cannot, just because physics says so. The other thing that we talked about in between this and this are the Schrodinger equations. We said, ooh, look, that's a pretty equation. We're never going to solve that. That is not for this class right now. The Schrodinger equation describes why we move away from waves to pictures, right? Remember when we talked about, okay, so this is how particles can move. They move as waves or they move as particles, right? Same, there's some kind of in-between. Then we talked about electrons, and we said, all right, so here's a three-dimensional atom, okay? We cannot know the exact position and the exact speed of an electron because it moves too fast and it's moving very rapidly, right? But we can measure several positions and try to get an idea of the boundaries of the electron's movement. And that's where we saw these cool probability diagrams. Anybody remember our probability diagrams? Right? They had these like kind of fading as you got away from the center. You know what I'm talking about? Right? This is an s orbital. We typically call it a spherical orbital for a reason, because when we tried to measure where the electron is in these probability diagrams, we noticed that they don't really get too far away from the nucleus. They tend to stay in the spherical area around the nucleus. Okay? The size of the orbital is given by the principal quantum number. And the size of that orbital gets larger as we move from one up. Okay? Now we can talk about quantum numbers. What was the rule for n? Do you remember what the rule for n was? What values could it have?
Oh, I think you go for 0 over 1.
N equals 1 up to whatever number it wanted. Does it have to be a whole number?
Yes.
Yes. Yup. So there's our first one. Woo, N. Sorry, say again? Oh, sorry, QN is quantum numbers. All right, so you've seen this before, right? What's this? That isn't an s orbital. Specifically, what is this notation? An electron configuration. In our electron configurations, we always start with the first number. That first number is the n value. All right? The next one is the L value. What does L indicate? I don't really care about the name of it. I think it's the angular momentum, whatever. what does it tell us?
The angle.
It tells us shape, right? L gives us a number that indicates SPDF. Right? L gives us the shape of the orbital. It is going to be all values that range from 0 up to n minus 1. If n minus 1 is 0, the only L value then is 0. We also made a handy little table where we had an L value and a shape. So an L of 0 is what shape? S, the simplest. An L of 1 is P, 2, and 3. Did we ever go beyond 3?
No.
That's G, right?
You would say G, sure. Postulated, not really. Okay. Remember that an s orbital is the sphere. P orbitals are the dumbbells. D orbitals look like a flower with a missing petal. Four-leaf clover without the stem. How about that? And then the f orbital is two d orbitals smooshed together. Attached at the center. Okay? All right. M sub L. What does that one tell us?
Magnetic.
Say again?
The magnetic property.
Sure. What is it?
3D space.
Orientation in 3D space.
Yep, that's what I meant.
In other words, how many different ways can we align that particular orbital diagram or that probability map so that we can see electrons in different ways? Okay? The rule for M sub L values is that they range, all whole numbers, from negative L to 0 to positive L. If L is 0, what is the value of M sub L?
Negative.
0. Okay? So if L is 1, what are M sub L values? There you go. So 3 orientations for a p orbital. Remember that? All right, last one. Spin quantum number. Spin. Spin is either positive or negative. We say spin up, spin down. This is why we draw arrows the way we draw them when we put them in orbital diagrams. Spin up or spin down. The rule. Oops. Positive 1/2, negative 1/2 for each ML. Each individual ML value is positive and negative. So, there were rules that went along with our quantum numbers. Pauli exclusion principle, the Aufbau principle, etc., etc. All those rules combined tell us, 1, how many electrons can belong to a set number of ML values, right? So for instance, if we have an s orbital, how many total electrons can we put in an s orbital? 2. If we had p orbitals, there's 3 p orbitals, how many total electrons? 6. If I had d orbitals, there's 5, how many total electrons? Etc., etc., etc. These rules all tell us why each orbital individually can only hold 2 electrons. That's our spin. Okay? These orbitals tell us that no 2 electrons can have the same exact 4 quantum numbers. One thing must be different. One thing must be different. A lot of times the thing that is different is the MS value, right? spin up, spin down. Then we move to the next box. Does that make sense? The rules also tell us that we fill from lowest energy to highest energy. So we fill 1s orbitals before we try to fill 2s orbitals, and so on and so forth. Remind yourself of these rules. Okay, what else? In chapter 6. Any questions from chapter 6 in front of you that you want me to go over specifically? If not, let's talk about periodic trends. I don't know what time it is. Oh, yeah. I will give you a break today, I promise. Periodic properties. All right, so first things first, we talked about effective nuclear charge. Also known as Z effective. Say again? Yeah. So this was calculated taking total electrons minus shielded electrons. And the term shielded means anything that comes in the row before. So when we say shielded electrons, we mean anything that can be indicated by the previous row's noble gas. So the reason why we can write noble gas notation is because everything that comes before the row that we're trying to talk about, where the electron is located in whatever row we're trying to talk about, all of these are shielded electrons. They can be mostly ignored for the purposes of any discussion we want to have. They can be ignored for the purposes of bonding. They can be ignored for the purposes of properties. They are just there to support the inner part of that atom. Okay? And that's what that term shielded means. So Z effective is essentially going to be equal to the valence electrons that your atom has to work with. Okay? All right. What's next? Ooh. Trying to do an effective nuclear charge. Nah. Trying to do atomic radius. Okay, here we go. As we move left to right. The atomic radius decreases. Do you remember how an atomic radius is measured? Anybody? Go ahead.
It basically is half the distance between the nucleus and the outer electron, correct?
Half the distance between the nucleus of two covalently,
Oh, all right.
you're fine, bonded identical atoms. So in other words, if I want to know the sodium atomic radius, I'm going to take 1/2 the distance between two of them bonded together, and I'm going to measure from nucleus to nucleus in order to take a half that distance. You were close. You were there. All right, left to right, atomic radius decreases. Why?
Because there's a stronger attractive force between the atoms, basically, because more electrons.
That's absolutely correct. Attraction between the nucleus and outer electrons gets stronger. As we move left to right, these are going to shrink. Everything's being pulled in more and more and more towards that nucleus. The nucleus is getting stronger. It's adding a proton as it moves left to right. So it's getting a more positive charge. And the outer electron cloud is also getting stronger. We're adding one electron, right, as we move left to right. And because we're adding those one at a time, we're seeing more and more attractive forces on the outside, which pulls things in closer, okay? As we move top to bottom. What happens? What happens to the atomic radius as you go down? Yeah, it goes up. Why? Not, I mean, yes, technically, but why?
Because you add another valence ring or whatever
Right.
it's called.
So we're getting further away, right? As we move down, we're adding more energy levels. So think like paper mache. It's my favorite analogy. As we move down, we're adding more and more layers, like an onion. And this is where we also technically said stuff. Remember I said the stuff argument. Don't use the stuff argument, but we are adding more and more stuff as we move down. All right, take a 5-minute break. I'm going to take a 5-minute break.